Hi everybody, we're going to be moving on with electric potential energy, and this is the last part of the voltage and electric potential module. So if you haven't done the reading, again, read Coletta chapter 18. In OpenStax chapter 7, in the college physics OpenStax. University Physics OpenStax, that's also Chapter 7. This is related to Homework 5 in Physics 112 and Homework 6 in Physics 131. So now we've got a clear view of all of the interrelationships between force and potential energy from the from 3.3. And what we found is that if you just integrate force with respect to x, you could get potential energy, and that's how you get this, and define force that way. We've known about the relationship between electric fields and force from Module 7, and from earlier in Module 3. I'm sorry, I said Module 7. I mean Module 2. That's the interrelationship between that. The relationship between electric fields and voltage was established earlier in the same Module 3. And in the last activity, we established the relationship between voltage and potential energy. Okay? So what we're going to be doing is using potential energy now, just like we did in Physics 121. We're going to be using energy to solve equations. And so now we're adding on the electric potential energy, which is Q delta V. All right. So there's a method. Again, we're going to be applying the conservation of energy. The initial energy is equal to the final energy. And we're going to be using basically the same method that we did in 121. And so we're going to be applying the conservation of energy. Energy in is equal to the energy out. Unless energy is lost, then the change in energy is, the difference in energies is equal to the energy lost from the system. There are different types of mechanical energies. Of course, we've learned that the whole point of doing this is kinetic energy. Kinetic energy is the energy of motion. Anything that has a velocity or a speed will have this energy. It's got 1/2 mv squared. Now we have a third initial potential energy. So the stored energy in a system is, there's one type that we learned in 121, which is gravitational potential energy, U sub G, and that's equal to mgh. It's the energy of height, simply just to severely reduce the sound. We learned also in 121 that that spring energy was another type of stored energy. That is 1/2 times the spring constant times the deviation from the equilibrium position for the spring squared. So that's 1/2 kx squared. And so that, in a way, that's kind of like a spring energy. Okay. Finally, we also learned that there's in 3.3 that there is an electric potential energy, and that is a charge within a voltage being moved. So that is also another type of stored energy. There's other types of energies which one can be considered just work, which is a force times a distance, times a change in the distance. And friction, I consider another type of energy. It's not a stored energy. It's something that, so work, how I define work here is, this is like a force of a hand moving an object or an outside force of some type, a rope, things like that. So it's a contact force times a change in distance. Frictional force is a unique type of force, is a unique type of energy which takes energy away from the system. Okay, if we're talking about kinetic friction, all right. And kinetic friction is the frictional force times the change in distance. So it's mu sub k times the normal force times whatever distance that friction is being applied to the object. When it gets moved from the system, it turns into heat, which can be viewed as like an internal energy to the object. So friction, something slides across the floor. The kinetic energy gets drained from the system, and gets changed into heat, which then heats up the object. And in a way, that's kind of like an internal energy to the system. And so let's go ahead and move on to the lecture tutorials. And let's work with all of these different types of energies. All right. So here we have a problem, and we're going to do just a really simple problem right in the beginning. We have a positive 1Q charge causing a voltage, emanating an electric field in all directions. And in this case, it's going to be creating a voltage. This voltage is going to be interacting with a cart, which has 5 charges built up on it. It's a cart that does have a mass too, and it has no initial velocity. Later on, the problem, the cart is now 2 meters away, and it's still got a voltage being applied to it, and it is now moving at a rapid speed. So take a look at your notes from 121 and try and approach this problem. We learned 2 different approaches in 121, energy pie charts and energy bar charts. You're welcome to do one or the other, but I want to do both of them so that way I could teach you guys, teach everybody both systems, and that way you could choose which system works best for you. All right. Eventually, what we're going to do is use these charts to create equations. All right. So right now, what I want you to do is think about the types of energies that are being applied to this in this initial case when the cart is at 1 meter, and then in the final case. So take a look at our earlier slide, which is right here, and think about the different types of energies, and type the energy in the beginning, type the energy at the end, apply that to your pie chart initial, pie chart final, and bar chart initial and bar chart final. Okay, so go ahead and try that. And hit pause when you hit pause and try that right now. Thank you. So we're back. So let's think about the types of energy that is being applied to the cart initially. And actually also the kind of level of energy that we're going to be working with. Okay. So initially the cart is right here at the 1 meter mark, and it is not moving. So the cart has no kinetic energy. It is not a height off the ground. This 1Q charge is creating a voltage at the 1 meter mark. Okay, so it does have electric potential energy. There's no springs attached to it. There's no outside forces like a hand or a rope pulling on it or pushing on it. And this case is a frictionless case. Mu sub k is equal to 0. So there is no friction. Friction isn't converting the kinetic energy into heat. So basically what we're dealing with is the electric potential energy at this point and no kinetic energy. So I'm going to go ahead and down to here, and I'm going to mark up the document. I'm going to go to comments. All right, and then I put that back, and now my tools have popped out. I am going to use black as kinetic energy because that's the whole point of what we're doing. And I'm going to use red as electric potential energy. Okay. So in the beginning, in this initial pie chart, it's got no velocity, it's not a height off the ground. There is no friction, there is no springs, there is no forces, outside forces. The only thing that is working on this object is potential energy due to electricity. So U sub Q. And I'm going to put a little I initially here. So this entire pie chart is filled with it's just electric potential energy at this 1 meter mark. So it's a voltage, it's a Q times V at that 1 meter mark. Okay. So let's go over to here. No kinetic energy, no gravity, no spring energy, no frictional energy. So it's a U sub Q, and I don't know what the levels of this should be. So I'm just going to give this 3 blocks. 1, 2, 3. So this is 3 blocks of electric potential energy. Okay. Cool. I got the first part done. The next part. Well, the object is moving now. So it does have a kinetic energy. It's still not a height off the ground. There's no springs attached to it. There's no outside forces attached to this, pushing it or pulling it. Friction, it's still on a frictionless plane. So there's no internal energy. There's no friction converting it to heat and then internal energy. But there still is an electric potential energy, but since it's further away, the voltage has decreased, right? This positive guy right here is causing a weaker potential energy, right? The further you get away from here, the weaker the voltage. So I'm going to say this, that the electric potential energy final is substantially smaller. Okay, and this is subjective, but so this is subjective. But I'm thinking that most of this initial energy got converted to kinetic energy. So now I'm going to use this. I'm going to use black, and I'm going to write kinetic energy here. So it's going to have a kinetic energy final. And it has a Q final. Well, over here, the kinetic energy final is 2/3. And again, I'm just making a guess as to the size. I'm just trying to represent the energy consistent with the initial energy. And the electric potential energy is much smaller over here. So it's only 1 block. Cool. Well, let's check our work. The initial pie chart is the same size as the final pie chart. So in this case, since there is no friction, there is no energy lost or anything like that. But even if there was, we could account for it in here. So I guess what the 2 pie charts being the same size is saying is that energy is conserved. And since energy is conserved in this case too, the 3 blocks positive here of positive energy should be equal to 3 blocks positive energy over here. Well, 1, 2, 3 blocks there, 1, 2 block here, and 1 block here. Okay. So again, this is a subjective point of view. All right. So if you're in Physics 101, this is what we're looking for as pie charts and bar charts. It's not necessary for you to create the equations, but you can do that, and we'll go ahead and do that on the next page. Oh, I forgot to do something. I'm sorry. Make sure you put your name in on the lecture tutorials, and so that when you could save it as you mark it up. Okay. All right. Well, now I'm over here. This is the same problem. I've just moved the pie charts around so that we could do it over here. So I'm going to choose this again, and I'm just going to really quickly create those pie charts again. Initially, this had a voltage working on our 5Q charges, right? So as Q initial. And then in the end, we had U sub Q final. And initially, we had 3 blocks of electric potential energy. And final, we had only 1 block. So I'm just recreating what we just did. And then when we use kinetic energy, I'm going to use black and try to be consistent about using black here. We had a final kinetic energy because it had a velocity in the end. And we only gave 2 blocks of energy here. Okay. All right, there we go. So now let's convert both of these things to equations. Okay. So what I'm going to do is I'm going to go ahead and start off with my initial energy. So initial energy is equal to final energy. So U Q I initially right here and right here is equal to U Q F, right? So it's equal to UQF, and in this final pie chart there's also kinetic energy here too, plus K final. Okay, K final. Okay, now that's our initial energy. So what we're doing is we're setting our initial energy. Okay, and I should have done that. I should have said started off with energy initial is equal to energy final. I apologize. I skipped a step. And now the initial energy was all U sub Qi. The final energy is a combination of kinetic energy final and U sub Qf. Okay. Well, U sub Qi is equal to Q. It's actually, so our object being moved was a 5Q object. So U sub Qi is the charge of the object that we're looking at the energy on, times the voltage being applied to it, and the voltage is being applied to it due to this 1Q charge. So the 5Q chart is moving in a field created by due to an initial voltage created by this 1Q object, and that's going to be equal to the 5Q charge moving further away in a final voltage over here. So now this 1Q object is creating a final voltage right here. In fact, I'll draw that right there just to make sure that we have this. So this 1Q object right here this 1Q object is creating an initial voltage here, and later on is creating a final voltage here. Now, initially this voltage right here, due to this 1Q object, is going to be K times our 1Q object, which is a positive object, divided by it's 1 meter away, right? It's 1 meter, this voltage line is at the 1 meter mark. In the end, this is going to be, again, our K times our positive 1Q block, creating a voltage now out here 2 meters away. Okay, so that's how we'll define our final voltages and initial voltages. The cart in the end also has a kinetic energy. That's 1/2 mv final squared. And I'll just put brackets around it. And so I guess we're going to have to use a little caret in this area right here. It's 1/2 mv final squared. Okay. And what we had also, so now that we have that, let's go ahead and define the voltage. We haven't completed this. We need everything to be in the basic levels of just distance, charges, velocities, and masses. You can't have voltage here. So we have to use our voltages that we defined up here for this area right here. So the 5Q hasn't changed, but now we have a voltage, which is going to be K times the 1Q charge. So that's going to be just KQ divided by 1 meter away. Okay. And so that's the initial voltage right here. The final voltage is, the final potential energy is 5Q times the final voltage, which is up here, which is KQ divided by 2 meters away, plus our kinetic energy, 1/2 mv final squared. Okay. So once we have this energy defined, what we can do is go ahead and solve for one of these objects. Like, what if I gave you the amount of charge, right, of each object of the, this is a one, so let's just say these are protons, so that this would be, Q would be 1.6 times 10 to the negative 19th positive. And if I gave you the mass, I could have you solve for the final velocity, right? So there's a lot of cool things that you can do with this, right? In fact, let's do a problem. Okay, here we go. Here's an example problem. We have a proton that has a speed of 3.5 times 10 to the 5th meters per second at a point where the electric potential is 600 volts. It moves through a point where the electric potential is 1000 volts. What is its speed at the second point? Okay. Well, I am going to mark this document up. I'm going to move that back. And I'm going to go ahead and create some pie charts. All right. So here we go. So the pie chart we're going to use initially, what they're saying is the object's got an initial pie chart. And it's got a final pie chart. And this represents the initial energy. This represents the final energy. So initially it's got some kinetic energy. And in the end, it's at a higher voltage. So it's a proton moving from a low voltage to a high voltage. My guess is the kinetic energy is going to get smaller. So K final is going to be a smaller slice. Okay. In fact, what I'm going to redo, I'm going to redraw all this. And I'm going to make bigger pie charts so everything's more clear. So this pie chart is the same size as this other circle. About the same size, right? Got to be consistent with conservation of energy. So I'm going to make this initial kinetic energy visibly larger and the final kinetic energy much smaller. Okay. I'm just taking a guess whether that's true or not. In the end, so in the beginning, it's got an initial potential energy due to a Q. And in the end, it's got a final potential energy due to a Q. Okay? Well, now let's create some equations from this. Start off with the conservation of energy. Now we're going to go ahead and input the energies that we see in our initial pie chart. Ki plus U sub Qi equals Kf plus U sub Qf. Right? Now, this proton, it has the mass of a proton, so it's 1/2 mass of the proton times its initial velocity squared. And I don't think I'm going to have enough room, so I'm going to bring that all the way over here. So 1/2 mass of a proton times the initial velocity squared. Remember, it's probably going to be a larger number, but again, this is subjective. I may be wrong. The math will work it out. In the end, this proton, this positive proton, is going to have a voltage applied to it of 600 volts. So this is the initial voltage. Okay. I'm putting a little right here, put little hats on this part to differentiate it from the initial speed. The final velocity is going to be the mass of the proton times the final velocity squared plus the proton times its final velocity, final voltage. All right. So in this problem, we are going to be solving for the final velocity here. So in order to do that, I'm going to take this energy, this final electric potential energy, and bring it on over to the other side. So I'm going to subtract it from both sides. So I'm going to write out the initial kinetic energy, which is 1/2 the mass of the proton times the initial velocity squared plus the initial potential energy minus the final potential energy equals 1/2 times the mass of the proton times the final velocity squared. I'm going to do this in equation form first before I put in my numbers. Okay? By the way, this right here, we could actually just look at it and just call it the mass of a proton over 2 times the final velocity squared, right? And that's going to help when we do a little bit of algebra here in the next part. So we need to get this, we need to isolate the final velocity. So we have to multiply both sides by 2 and divide both sides by the mass of the proton. In a way, you could imagine this is flip-flopping onto the other side. So it's going to flip-flop, and 2 is going to now be on top, right? Multiply both sides by 2, divide both sides by the mass of the proton, and this side right here is going to now be in parentheses. Gotta remember to copy it just as I see it from right above. and that's equal to the final velocity squared. Square root both sides. So I'm going to square root this guy, and then square root this other side. When we square root this other side, this disappears. There we go. So now we have an equation representing the final velocity. So we just have to input our numbers here, okay? So let's go ahead and do that. This is going to be a huge problem. So we're going to put in 2 divided by 1.67 times 10 to the negative 27th kilograms is the mass of a proton. We're going to times that by 1/2 times the mass of a proton, which is again 1.67 times 10 to the negative 27 kilograms, times the initial velocity squared, and they said the initial velocity, so I'm just copying this part here. The initial velocity is 3.5 times 10 to the 5th meters per second squared. Oh boy, this is getting crazy. This Q right here is the charge of a proton, which is 1.6 times 10 to the negative 19 coulombs. So that's this charge. Now we've got to put the velocity there. We're going to multiply by the initial, velocity, voltage. The voltage is 600 volts. And we're going to subtract from that the final. I should be careful here. I actually didn't copy this as it is. I should have been subtracting off that final. Sorry about that. That final guy is just right there. It's just a negative. I forgot I had to subtract that off from there, which is going to be 1.67. Again, is the charge of a proton times 10 to the negative 19 coulombs times 1,000 volts. And that is our final velocity. Okay? So let's go ahead and put that into our calculators. And what I get looks like it's going to be 0.45 times 10 to the 11th meters per second. All right. So that's how you use pie charts and bar charts to create equations. And then start adding level of details to the equations, and then input in any variables that you are given for define any variables that are given, and solve for something that is being asked. So this is our solution. Okay. So that is a problem where you have 2 point charges interacting with each other. Now let's try another problem where we've got an electric field causing the same situation as before. It'd be causing the same situation as here. So it's the same problem, but now instead of a little block causing a voltage at this point and a voltage at this point over here, we're going to have an electric field. So let's talk about it. All right. Well, we had learned that So here we have a 5Q cart, same thing on a frictionless surface. It starts out at the 1 meter mark with no initial velocity. Okay. And in the end, it's got a final velocity here. Okay. And it's also still in an electric field that is 2 newtons per coulomb field. So go ahead and draw the initial pie chart and final pie chart, as well as the initial bar chart and final bar chart. So take some moments and draw that right now. Hit pause, please. All right, here we go. So initially, this is going to have an initial voltage on it, since it's in an electric field. So that's an initial voltage. And in the end, it's still in that electric field, so it's going to have a final voltage on it. Okay. It's not moving initially, and in the end, it is moving. All right. So let's go ahead and just say it's got an initial potential energy due to electricity. And in the end, since it is moving, and since that voltage is decreasing over as we're moving to the right, we're going to be at a lower potential energy due to electricity. And the object is going to have some type of speed. So let's try it here. Let's say that this has an initial potential energy, and we'll just give it the same amount of blocks that it had before. And in the end, the potential energy is dropped off. I don't know how much it's dropped off. This is a subjective judgment, as is the proportions over here. And let's say it's dropped off by 1 block. Well, it started off with 3 blocks. It's got 1 block, and since energy has to be conserved in this case, there's no friction, then that means there's two blocks of kinetic energy. So 2/3 of the initial energy got converted, in my judgment, to this to kinetic energy. And that's a subjective, I shouldn't say judgment, I should say opinion. Okay, and I'm just illustrating this to show a point. All right, and I should use black for the kinetic energy. So, got to use black for that kinetic energy. Okay. Well, we've created an interpretation of the change of energy from the initial to the final. Let's go ahead and move on to the next part here and convert these to equations. All right. So if you're in Physics 111, Physics 121, move on to the next page, and let's go ahead and convert these to equations. So I'm going to go ahead and copy down what we did before. Okay. All right, let me do a better job at copying that down, what we did before. So we had we had final kinetic energy that had 2 blocks, and we had this as K final, and then, oops, let's go ahead and draw the potential energy. So initially it had an initial potential energy, and here it had a final potential energy that was smaller because the voltage is dropping off. It's decreasing as a positive charge moves downhill. So the initial voltage here is greater than the final voltage here. Okay. So the initial voltage is creating a higher potential energy, acting on our 5Q cart, and it's getting that initial potential energy due to electricity is being converted to kinetic energy, but it has not all been converted. Okay. So let's go ahead and draw our, let's go ahead and write our equations, okay? So in this area right here, I'm going to start off and I'm going to say initial energy is equal to final energy. Whoops, didn't mean to bring that up. Well, I erased all that. Initial energy is equal to final energy. All right. Now, in the end, so let's look at what our initial energy is. Our initial energy is UQI. So I'm just going to copy that down. And in the end, it's equal to UQF. So it's got a final potential energy. And it's got a final kinetic energy. Okay. Initial energy, final energy, just double checked it. Okay, cool. Well, let's start putting in our variables. Let's start putting in our levels of let's put in our levels of detail. Okay. So initially, this is going to be a 5Q cart, and I'm going to put a positive 5Q cart, and it has an initial voltage working on it. Okay, and so that is the initial potential energy. And let's give us some space here. Okay. Well, in the end, that it's got a positive 5Q cart, and it's got initial potential working on it, or voltage working on it. The same 5Q cart has a final voltage working on it, and it is moving. And that's the mass of the 5Q cart, which I don't know what that is, but it does have a final velocity that is being squared. Cool. Well, let's talk about the voltage, the initial voltage. Now, it's weird to calculate the change in energy, you need a change in voltage. So you can't just calculate the voltage right at this point, right? So, well, I suppose we can define that as, we can say that this initial voltage is equal to the electric field times the initial position, the 1 meter mark. I guess we could say that. Even though this is delta V, this is supposed to be delta V equals the electric field times delta R. All right. But we're going to let those deltas come out when we're dividing the voltages on both sides. In the end, that final voltage, okay, that final voltage is going to be, again, the electric field times the position of the 2 meter mark. Okay. And so that initial voltage is going to be equal to 2 newtons per coulomb times 1 meter. And that final voltage is going to be 2 newtons per coulomb times 2 meters. And that's the final voltage. Okay? Well, since we have such a clear definition of the initial and final voltage, really the only thing to solve for is the final velocity, most likely, if you're going to be doing this problem. So let's go ahead and put those numbers into here. So this is going to be a 5Q, and that's initially, that's going to be 2 newtons per coulomb times 1 meter. And that's equal to our positive 5Q times our electric field, which is, again, 2 newtons per coulomb, times the position at the 2 meter mark, plus 1/2 m. You know what? I'll just copy this, plus this. All right. So now we can go ahead and solve for Q. Since we only have one equation, we could only solve for one unknown. We could solve for the final velocity. We could solve for a lot of really neat stuff. All right. So this is a really cool problem. Let's do one last problem, and then you'll have to complete the rest of the lecture tutorial. Okay, and I've gotten you started on it. So go ahead and let's try this one. All right. So you have a positive charge in an electric field. It starts out at a position of 0 meters, okay, which is weird. That means the voltage is going to probably be 0. We're gonna have to use the positions to calculate the voltage differential. So kind of interesting. So it starts off at a position of 0. So this object is at a position of 0. It's going to slide, so initially not moving. Then the electric field is going to be applying a voltage to it at this position and start moving it to the right. Okay. And as it moves to the right, it's going to hit this area of friction. And it's going to speed up, but then it's going to hit this area of friction, and that's probably going to cause some of that kinetic energy to get converted to potential so that friction is going to cause some of that kinetic energy to be converted into heat, and thus internal energy to the system. And then it's going to leave here, and it's going to then hit another area of no friction, and then keep moving until finally it's at a position of 3 meters. It is moving, and there is a final voltage on it. So the first things I'm going to do is I'm going to go ahead and I'm going to draw the voltage lines. I'm going to draw that this has got an initial voltage on it, and over here it's got a final voltage on it, because that's what I said. It's got a velocity here, and this is a 1Q charge, but also there was some heat. So some of that work due to friction got converted to heat, which in our case we're going to call an internal energy. Okay? So, in fact, what I'm going to do is I'm going to call that blue. I'm going to call that stuff, I'm going to redraw that, and I'm going to call that blue. I'm going to call friction blue. All right. So a little bit of friction, work due to friction. So that frictional force, that non-conservative frictional force, is taking kinetic energy out of the system, right? It slowed it down. Even though technically the friction is not working on it right here, it was working on it right here and bleeding off the kinetic energy. It converted that kinetic energy to friction. Okay, well, to heat through friction, which then left the system. Well, now it is now permanently heated up the object, right? So I'm going to keep it in the system, but as like an internal energy. It's heated this object, okay? So this object is kind of radiating heat now, okay, where it wasn't radiating any heat in the beginning. So now that I've kind of analyzed my problem, let's go ahead and let's start drawing our pie charts. Well, initially I'm going to say it wasn't moving. It wasn't a height off the ground. So it wasn't moving. It wasn't a height off the ground. There was no springs attached to it. No outside forces working on it. Friction hasn't been working on it yet. There's no heat. It's just all initial potential energy due to electricity. Now again, the voltage is decreasing over time, and this is a positive object, so that means the final potential energy is going to be smaller. Okay. Not only that, so we have the initial potential energy, and I think we have the initial pie chart done. So I'm actually going to go ahead and draw the bar chart to this. And I don't know how much energy that is. This is, again, is subjective. But I know all of that energy, and I'm going to give it 4 blocks, is going to be, I should have put it here under this area. There we go. 4 blocks of initial energy. Subjective, I don't know. And same thing with this final slice of that initial energy. That final potential energy due to electricity. Let's go ahead and put in the friction. So I'm imagining this area right here bled off a lot of friction, a lot of energy to friction. And now it's radiating this heat, okay, which is blue. Well, I'm imagining this is how much energy that got turned into heat from the friction, right? It then began to speed up again. So what I'm guessing also is that the rest of the energy, come on. The rest of this energy, whoops, is now kinetic energy, right? So in the end, I'm going to say this, it's got a lot of heat energy, it's got a lot of kinetic energy, and I'm going to give it let's give it 2 blocks. Don't be too greedy. So, and this is subjective. And I'm going to just say that one of those blocks is our heat that friction turned that kinetic energy that friction turned into heat, and 1 block of potential energy due to electricity. So that's kind of what I'm imagining as the pie charts, okay, and bar charts. So if you're in Physics 101, go ahead and stop here. This is good enough. If you're in 112 and 131, move on to the next part, and you're going to have to convert these to equations. So let's do it. All right, here we go. I'm going to try to recreate what we just did. UQI and UQF. And I'm going to give this all 4 blocks, 1 block, and I think I said that this was the friction that got converted into heat, and this was 1 block. And that kinetic energy is 2 blocks. So this is an interesting problem because it, again, is going to illustrate how you could only get how potential energy is a change in voltages. Okay, so weirdly enough, it's going to, you'll see what I'm talking about. So we're going to go ahead and talk about the voltage right here at this point. Okay, and that is our initial voltage. All right. And it's going to have a final voltage at this point right here. Okay, well, earlier we said the initial voltage is, if we're in an electric field, is the electric field times its initial position. Okay, and over here, the final voltage, right here, is going to be the electric field times its position, our final, and this is our initial. Well, the electric field is 2 newtons per coulomb, and the initial position is 0 meters, which is, this is going to be weird, but our initial voltage is 0 volts. Okay, which basically is, it sounds like it's not, it's actually not, has no initial energy. But that's going to get taken care of when we calculate the change in voltage, right? Here in the end, it's got 2 newtons per coulomb, and the final position is 3 meters. And what I'm going to do is I'm going to keep this in the equation, this initial voltage, right? And then when we bring it on to the other side and solve for like the final velocity or something like that, and I got to remember to put the little tops on these guys. So differentiate voltage from velocity. That when we calculate the final velocity of something, it's actually going to be v final minus v initial. Okay, so I'll show you what our v initial minus v final. So we'll talk about it. Okay, so let's start off with our equations. Initial energy, always start here, is equal to final energy. And let's go ahead and start off. This is a 1Q object, so it's a positive 1Q object times V initial. And that's going to be equal to the 1Q object times V final plus our heat energy, which is going to be mu sub k, so little u sub k times the normal force that's the frictional force times the distance that it changed, it went across this distance. Well, the distance was 2 meters minus 1 meter. Okay. And this is going to be plus the final kinetic energy, which is 1/2 mv final squared. So notice I skipped a step, and I'm sorry I did that. I probably should have, just overtly written out these energies, and I'll do that now. But this initial part right here is U QI, and that's equal to UQF plus the internal energy. In this case, the internal energy is the frictional force times the change in distance, plus 1/2 times mass times final velocity squared. Okay? And I'll put brackets around that. So let's say we had to solve for the final velocity, all right? And actually, let's just say we had to solve for the final kinetic energy. Well, we're going to keep the initial energy onto this side, positive 1 q vi. And we're going to subtract from that, we're going to bring, oops, I forgot the q on there. We're going to bring this final potential energy due to electricity onto the other side, which is, we're going to subtract that from both sides. That's a positive 1q times the final voltage. Okay. And then we're going to subtract again. We're going to subtract this, our internal energy, or our frictional energy, if you want to call it that, times the normal force. And the normal force in this case, since it's on horizontal ground, just draw a little quick force diagram here. We have our little charge that has a mass on the ground. It's got a normal force up. It's got mass times gravity down. So since it's not accelerating or moving in the y direction, then the normal force is going to be equal to the weight of the object, which is just going to be mg. Okay. So then what we could do is just call that normal force mg times 2 meters minus 1 meter. And that's going to be equal to our kinetic energy. Okay. Now, what we had talked about before is that the initial voltage is going to be 0. Okay. And really, again, what I had stated is that we actually have to look at potential energy as, so what I'm going to do is merge these two equations together. Okay. And in fact, I'm going to do this. Merge these two equations together to illustrate my point. I'm going to pull out a positive 1q, all right? And that's going to be equal to v sub I minus v sub f. So again, just like the earlier lecture, the only way to measure electric potential energy is by a change in voltage. That's why it's so important to get a delta V, because potential energy is equal to Q delta V, right? And since you can't say that we started out with 0 energy, even though this works out to be 0, that had to be something that drew that across. And it was actually the change in energy that is causing it to move. And it's a change in voltage, okay? And so that's being illustrated from here, okay? Where V final is going to be 6 Newton meters per Coulomb, and V initial will be 0. It's actually the change in voltage, okay? I'm going to subtract off our frictional coefficient. And multiply it by mg, and in this case 2 meters minus 1 meter. I'll just leave it like that. Equals 1/2 mv final. You know what? I'll just copy this and paste it right here. So what I want you to do now that we've gone through the process of analyzing these energies is please complete the rest of these lecture tutorials, okay? So go through all of them. And again, in the homework of homework 5.07 in Physics 112 and homework 6.06 in Physics 131 is related to what we're doing right now. Other problems in those homeworks are related, but this one is really what we're looking at. Okay? Good luck.